In this lecture, we will see how to solve systems of linear equations using augmented matrices. In so doing, we will encounter and use elementary row operations, row echelon form, and Gaussian elimination. Using worked examples, we will see how to deal with systems of equations that have no solutions, unique solutions, and infinitely many solutions. Recall that given a system of linear equations, we can summarize their information in a matrix equation. This presentation can be simplified further by writing the information in a single matrix called an augmented matrix. The vector x representing the unknown values is omitted, as is the equal sign, and a vertical dividing line separates the entries from the other two matrices. To refer to rows in an augmented matrix, we conventionally use the notation Ri, where I is the row number. To understand how to use the augmented matrix to solve a system of linear equations, let's first look at how the system is normally solved algebraically. Consider the system given by the equations 3x plus 2y equals 1 and 4x minus 3y equals 7. We can label these as equations 1 and 2. Let's multiply equation 2 through by the number 3. This gives 12x minus 9y equals 21, which we will label as equation 3. Now, let's find equation 3 minus 4 times equation 1. This gives negative 17y equals 17, which we will label as equation 4. From this equation 4, we know that y equals negative 1. Then, substituting y equals negative 1 into equation 1 gives that 3x equals 3. So altogether, we know that x equals 1 and y equals negative 1. Now, let's see how these steps are reflected in the augmented matrix. First, we multiply row 2 through by the number 3. Then, from row 2, we subtract 4 times row 1. Writing row 2 out in expanded equation form means 0x minus 17y equals 17, which tells us that y is negative 1. Writing row 1 out in expanded form means that 3x plus 2y equals 1. So we substitute y equals negative 1 into this equation to find 3x equals 3, and ultimately, the solution. Manipulating the rows of the augmented matrix in this way is a slightly simpler and quicker way of solving the system of equations. When solving systems of equations with augmented matrices in general, the steps taken to simplify the matrix are called elementary row operations. There are 3 types of elementary row operations that we can apply to an augmented matrix. Firstly, we can swap the positions of 2 rows at any time. This is written as a double-headed arrow between the 2 swapped rows. To show the operation being applied, we can write it atop an arrow from the original matrix to the modified one. In this example, row 2 is swapped with row 3. The second type of row operation allows us to multiply a row through by any non-zero constant. This is written as turning any row Ri into the scalar alpha times Ri. For example, we can multiply row 1 in this matrix through by the number 2. The final type of row operation allows us to add one row to the multiple of another row. This is written as turning any row Ri into Ri plus some scalar alpha times another row Rj. Note this can also be thought of as subtracting a multiple of one row from another whenever the scalar is negative. For example, we could subtract 2 lots of row 1 from row 2 to achieve this matrix. The 0 comes from 2 minus 2 lots of 1. The negative 1 comes from 3 minus 2 lots of 2, etc. Our goal in applying these elementary row operations is to make the augmented matrix simpler, so that the system's solutions can be easily deduced from it. So we should establish what makes an augmented matrix simple. We'll call the first non-zero entry in a row the leading entry of that row. A simplified matrix is said to be in row echelon form if in each row the leading entry is further to the right than in the previous row, and any rows without leading entries are grouped at the bottom of the matrix. For example, in this matrix, the leading entries are here, here, and here. Since they occur further to the right as we go down the rows, the the matrix is in row echelon form. In this matrix, the leading terms are here and here. Again, they appear further to the right as we go down the rows, and the row without a leading entry is found at the bottom. So this matrix is also in row echelon form. In this matrix, the leading entries are here, here, and here. In the third row, the leading entry is not to the right of the leading entry in row 2, nor to the right of the leading entry in row 1. So this matrix is not in row echelon form. In general, we will apply elementary row operations to an augmented matrix until it is in row echelon form. This whole process is called Gaussian elimination. Let's practice applying Gaussian elimination to an example augmented matrix. In this case, we'll use the 3x4 matrix with entries 3, 2, 8, 6, 1, 3, -2, 2, 5, 6, 0, 7. Our first goal is to make the first entry in the matrix a 1, if possible. In this case, swapping rows 1 and 2 will achieve this result. So our first elementary row operation will be to swap rows 1 and 2. Next, to ensure the other rows don't have leading entries in the first column, we should change the first entry in row 2 and the first entry in row 3 to zeros. Because the leading entry in row 1 is now a 1, this can be easily done. We can subtract 3 lots of row 1 from row 2 to eliminate this 3, and we can subtract 5 lots of row 1 from row 3 to eliminate this 5. Because these two row operations affect different rows, we can perform them simultaneously. Our next goal is to make the second leading entry in the matrix a 1, or close to 1 if possible. In this case, we can see that row 2 has a common factor of 7, so we can perform the row operation that multiplies row 2 by the scalar -1 on 7. Next, we need to ensure that the leading entry in row 3 is not in the second column. So, much like in step 2, we can add 9 lots of row 2 to row 3 to eliminate this -9. The resultant matrix has leading terms here, here, and here. So it is now in row echelon form. Once we have reduced an augmented matrix to row echelon form, we still need to find the solutions to the original system of equations. As we saw in the earlier example, this is done by rewriting the lower rows as equations and solving for the unknowns. We can actually deduce some properties of the solution set for a system of equations just by looking at the shape of the augmented matrix in row echelon form. There are 3 possible such scenarios. If the column right of the vertical line contains a leading entry, then we can immediately conclude that the system has no solutions, or we can say that the system is inconsistent. Otherwise, we will have a matrix in which there are no leading entries in the last column. Then, if all the columns left of the vertical line contain a leading entry, we can conclude that the system has a unique solution. Otherwise, if any columns left of the vertical line do not contain a leading entry, we can conclude that the system has infinitely many solutions. For example, the leading terms in this matrix are here, here, and here. The rightmost column contains a leading term, so the system will have no solutions. The leading terms in this matrix are here, here, and here. The rightmost column does not contain a leading term, so the system has at least one solution. Furthermore, all of the columns left of the vertical line contain a leading term, so the system has exactly one unique solution. The leading terms in this matrix are here and here. The rightmost column does not contain a leading term, so the system has at least one solution. Furthermore, there is a column left of the vertical line that doesn't contain a leading entry. So the system has infinitely many solutions. Next, we will go on to look at each scenario in detail by solving an example system of each type. Let's try solving the system of simultaneous equations 2x plus 6y plus 4z equals 12, 3x plus 5y plus 4z equals 10, and x plus y plus z equals 4. First, rewrite the system as an augmented matrix. Next, apply elementary row operations to the matrix until it is in row echelon form. First, we'll swap rows 1 and 3 to make the first entry in the matrix a 1. Then, we'll subtract multiples of row 1 from the other two rows so that their leading terms are no longer in the first column. At this point, we can see that subtracting two lots of row 2 from row 3 will ensure that row 3's leading term is not in the second column. So, applying this row operation produces this matrix in row echelon form. The leading entries in this matrix are here, here, and here. There is a leading entry in the rightmost column, so we can conclude that the system has no solutions. The reason for this is that rewriting row 3 as an equation translates to 0x plus 0y plus 0z equals 8, which is of course impossible. Now let's try solving this system of simultaneous equations, where x plus 3y plus 2z equals 4, 2x plus z equals 5, and 3x plus y plus 4z equals 10. First, rewrite the system as an augmented matrix. Notice here that because there is no y term in the second equation, we write that the coefficient of y is 0 in the augmented matrix. Next, let's perform Gaussian elimination on this matrix. Conveniently, the first entry in this matrix is already a 1, so we can subtract multiples of row 1 from the other two rows so that their leading terms are no longer in the first column. In this case, we'll subtract 2 lots of row 1 from row 2 and 3 lots of row 1 from row 3. Since there are now common factors evident in rows 2 and 3, let's next multiply row 2 by negative 1/3 and row 3 by negative 1/2. At this point, we can see that subtracting 2 lots of row 2 from row 3 will ensure that row 3's leading term is not in the second column. So applying this row operation produces this matrix in row echelon form. The leading entries in this matrix are here, here, and here. The rightmost column doesn't contain any leading entries, so we know there is at least one solution. Furthermore, all columns left of the vertical line contain leading entries, so we know that the system has a unique solution. It remains for us to actually find this solution. Reading off row 3, the corresponding equation is 0x plus 0y minus z equals negative 1. So we know that z is 1. Next, reading off row 2, we get the equation 0x plus 2y plus z equals 1. Substituting z equals 1 into this equation tells us that y equals 0. Finally, reading off row 1, we get the equation x plus 3y plus 2z equals 4. Substituting z equals 1 and y equals 0 into this equation tells us that x equals 2. So in conclusion, the solution to this system of equations is x equals 2, y equals 0, and z equals 1. Now let's try solving this system of simultaneous equations, given by 2x plus 3y plus z equals 4, x plus 2y plus 2z equals 5, and x plus 4y plus 8z equals 17. First, we rewrite the system as an augmented matrix. Next, we perform Gaussian elimination on this matrix. First, we'll swap rows 1 and 2 to make the first entry in the matrix a 1. Now, we can subtract multiples of row 1 from the other rows. In this case, we'll subtract 2 lots of row 1 from row 2 and 1 lot of row 1 from row 3. At this point, we can see that adding 2 lots of row 2 to row 3 will ensure that row 3's leading term is not in the second column. So applying this row operation produces this matrix in row echelon form. The leading entries in this matrix are here and here. The rightmost column doesn't contain any leading entries, so we know there is at least one solution. Furthermore, one of the columns left of the vertical line does not contain a leading entry. So we know that the system has infinitely many solutions. Now we need to find a way to express this infinite set of solutions. Since there is no leading term in the third column, and the third column corresponds with the unknown z, we'll say that z can take the value of any real number. We'll write this as z equals t, where t is any number in the reals. The notation here is shorthand for the sentence, t is a number belonging to the set of real numbers. Next, reading off row 2, we get the equation negative y minus 3z equals negative 6. Substituting z equals t into this equation tells us that y equals 6 minus 3t. so we are able to express both z and y in terms of t. Finally, reading off row 1, we get the equation x plus 2y plus 2z equals 5. Substituting z equals t and y equals 6 minus 3t into this equation tells us that x equals 4t minus 7. So now we have been able to express all the unknown variables in terms of just t. This means we've been able to find the infinite set of solutions to the system. So in conclusion, the solution to the system of equations is x equals 4t minus 7, y equals 6 minus 3t, and z equals t, where t is any real number. Let's finish off this section by looking at an example of a word problem. In this sort of question, a set of information must first be converted into a system of linear equations before we can solve the system. For example, in this problem, there are 3 people labeled A, B, and C, and each of them is an integer number of years old. We are asked to deduce their ages based on the fact that the sum of their ages is 72, that in 4 years, the sum of B and C's ages will equal A's age, and that 8 years ago, the sum of A and C's ages was 3 times B's age. First, let's let the ages of the people A, B, and C be the lowercase pronumerals A, B, and C. To extract the system of equations from this question, let's deal with each fact in turn. The first fact tells us that A plus B plus C equals 72. The second fact tells us that B plus 4 plus C plus 4 equals A plus 4. We want all the pronumerals grouped on one side of the equation, so let's rewrite this as A minus B minus C equals 4. The third fact tells us that A minus 8 plus C minus 8 is 3 times B minus 8. Rearranging, we get that A minus 3B plus C equals negative 8. We can now write these 3 equations as an augmented matrix and apply Gaussian elimination. Since the first entry is a 1, we can immediately remove the leading terms in rows 2 and 3 by subtracting a copy of row 1 from each of rows 2 and 3. Next, we can remove some common factors from rows 2 and 3 by multiplying them by negative 1/2 and negative 1/4 respectively. Finally, we can remove the leading term in row 3 by subtracting a copy of row 2 from row 3. This brings us to a matrix in row echelon form. The leading terms are here, here, and here. The rightmost column doesn't contain any leading terms, and each of the columns left of the vertical line does contain a leading term. So this system has a unique solution. The third row tells us that negative c equals negative 14, so we know that c is 14. The second row tells us that b plus c equals 34. So substituting c equals 14 into this equation tells us that b is 20. The first row tells us that a plus b plus c equals 72. So substituting c equals 14 and b equals 20 into this equation tells us that a equals 38. So in conclusion, we know the ages of a, b, and c are respectively 38, 20, and 14. In summary, we have learned about elementary row operations and how to apply them to an augmented matrix to achieve row echelon form. We have also seen how to deduce the number of solutions to a system of equations based on the shape of its augmented matrix in row echelon form, as well as how to completely solve systems in all 3 scenarios, when there are no solutions, when there is a unique solution, and when there are infinitely many solutions.